Let's get started. Whoever was signing the attendance roster as Billie Eilish in here would be happy to know that Luke Skywalker was in statics on Wednesday. This will get to be kind of fun. I just hope it doesn't get out of hand where they've got, like the entire Fellowship of the Ring on the roster or something. All right. I checked this morning, 5.3 still being graded, but the solution should be up. Other than that, we're current in here. We're up to date. 5.4 was due today. What'd you think of the Excel assignment? Hopefully that wasn't too bad. Hopefully it was easier than what we did in class. And 5.5 will be assigned today, due on the 11th. Now, a couple of things. Number one, if you look on Blackboard, there's a folder called Analysis Project. And inside that folder, not only is there the lecture notes from the Analysis Project from Lecture 15, but there's all of the data on the rolled shapes, which quite frankly won't matter for the first submission. And there's a submission form for that first submission. It's due Wednesday. A couple things, you can do that by hand. You can do that on CAD, however you want to do it. If you look, you know how I do a homework assignment, like I'll do it as like a little PDF and I'll say, textbook problem this, or like the last homework assignment where it was like a custom problem. You'll see a write-up of the first submission, and there's nothing, it's not like I was springing anything on that write-up that I didn't talk about in Lecture 15. I just thought, why don't I put everything that was relevant to the first submission on a single page? So that's all that is. And that's due Wednesday. Does anybody have any questions on that I can answer from the class as a whole? I don't think this first submission is going to take a lot of time. I just want you to come up with 3 conceptual truss layouts and pick one based on a given reason. Bless you. All right. Any questions? Okay. So we're rocking and rolling on shear and moment. We're still utilizing our relationship that the calculus-based relationship between loads, shears, and moments, that if you integrate loads, you get the shears, and if you integrate the shears, you get the moments. And that relationship led to a series of conclusions, right? And what I hope that you are starting to see is that even though we've taken the problems and ratcheted them up a bit, we had, point loads, then we have uniformly distributed loads, then we have triangular loads. We've taken the loads and ratcheted them up, but this hasn't changed. This has been the same. At any given point, the slope of the shear diagram is equal to the load, right? And in between 2 points, the change in shear is equal to the magnitude of load between those 2 points. And then at any given point, the slope of the moment diagram is equal to the shear. And between 2 points, the change in moment is equal to the area of the shear diagram. That hasn't changed. Even when we did the triangular load diagram, if you wanted to break out calculus and integrate that shear diagram, that shear function from 0 to whatever, that would give you the change in moment. What I want to do now is continue that discussion. I'm actually kind of bringing it backwards a little bit because, we started with no load, constant shear, linear moment, and then constant load, linear shear, quadratic moment, and then linear load, quadratic shear, cubic moment. Like we were ratcheting it up. Now I'm actually bringing it way back when we talk about concentrated moments. So concentrated moments, this is going to be kind of weird, okay? Because a concentrated moment is just that, a moment. It does not affect the shear diagram at all, okay? Concentrated moments are moments. They're not forces. Shear diagrams, we call it V, because it represents the change in vertical forces, okay? Forces. Because concentrated moments are not forces, they do not affect the construction of the shear diagram at all, okay? We're still going to integrate the shear diagram to construct the moment diagram, but we're gonna see something different happen. We're going to find out the areas don't match, or if you sum the areas, you're not going to get 0, okay? This is also going to affect cantilevered beams because, so we're going to do 2 examples today. This is example 4, this is example 5, and example 5 also has a concentrated moment because when you're dealing with a cantilevered beam like this, the cantilever, the fixed support, has 3 reactions, one of them being a concentrated moment. Okay, so we're going to do 2 problems today. Now, for both of these problems, I've given you the support reactions because we've already done these problems. Okay, we did the support reactions for these problems a while back. So what we've got here is a beam. This is an overhanging beam, and I like this problem because you know, I think that when you as a student first see this problem, you hear Dr. Mike saying, okay, today's lecture is about concentrated moments. So you look at the beam, and the first thing that you're paying attention to is this thing right here, this 20-foot kip moment, which is naturally what you should do. But the other point I want to mention is it's not like that's the only thing there. We have point loads, we have distributed loads, and so I want you to feel like you can handle all that stuff too, right? I don't want the old stuff to feel like it's impossible. It's like you see this, it's like this is the only thing that should be new. Everything else should be fine, okay? So I have an overhanging beam. It's 25 foot long on this span, 20 foot long on this span. On this end span, halfway across, I got a concentrated moment. And I've got 3 kips per foot over a little bit of the span over here. And I have my reactions already computed because we did this one before. I think this was like reactions example 4 or something like that. I'll give you a sec. I'm going to pull up my notebook, and I already have this in the notebook as well. Let's make this a little bigger. I'll give you a sec to copy this down, and then we will get to it. Okay. Is everybody good, or do you need me to give you a minute? I'm fine to give you a minute. It's okay. I still see some folks copying down. We'll take a little bit. We're in no hurry. We're in no hurry. All right. While you're doing that, let me get ready to construct the shear diagram. And you know that the way I'm going to do that is I'm going to draw my little, what is that? Okay. Draw my little guidelines. All right. So, come on. Okay. We start off by drawing the shear diagram, and just because we have a concentrated moment doesn't mean that our tenets don't hold true, that we have to start at 0 and end at 0. So I start at 0 over here on the left, and what do I do? What's the first thing that I do? If I start at 0, what does the beam tell me to do? To go up a magnitude of 15.2 Bless you. Now, if I go up 15.2, okay, so let's come up with some letters here. They're not all that necessary, but let's come up with some letters here. So we've got A and B. Let's call this C, D, and E. So from A to C, so we'll call this C. From A to C, what happens? It goes down 30. So if let's be clear, if I'm at 15.2 and I go down 30, where am I going to be right here? Negative 14.8. Now, what does the path look like from A to C? Linear. It's a straight line. So, sorry, I'm going to scroll a little bit and come back because that's going to be a sharp diagonal. I think that's about the best diagonal I could draw in that instance. So, negative 14.8. All right. What happens from C to B? Constant, zero slope. Just whoop, goes like that. Now what happens at B? So if I'm at negative 14.8, I jump up 24.8. What's that put me at? 10. From B to D, what's going on? Constant. Nothing. No change. What does that concentrated moment do to the shear diagram right here? Nothing. Not a thing. So from D to E, we just keep on trucking. And then this brings us back down to 0. That's your shear diagram. Right there. Now, let's see if we can come up with some areas. Okay? So we'll call this shape 1, 2, 3, 4, 5. Now, I'm an engineer. I don't think you need to be hyper systematic for everything. If there's something that you can just look at. What is the area of shape 3? Well, it's 14.8 times 15. What is that? Say it again. Negative 222. All right, what about shape 4? 100 and shape 5. 100, right? So, is that a fair statement? So, the only one that we kind of maybe need to do a little bit of figuring on is shapes 1 and 2. So, what do? We say, okay, x1, x2. Is that fair, right? And let's make sure that we're all paying attention over here. How do we determine x1? What's an easy way of determining x1? Anybody remember that? The height divided by the slope. So 15.2 divided by 3, right? And then this one's going to be 14.8 divided by 3. So okay, and so that ends up being like 5.067 . And that ends up being something like 4.933. Did I get that right? Yeah. Okay. So if that's the case, what's the area of shape 1? 38.5. I think it comes out like 38.51, something like it's something like that, right? And then this one, what's the area of that? 36.51? Negative, right? Is that okay? Now, what have we done so far before we move forward? What was our check? Like before we drew the moment diagram, we did something. What did we do? We summed up the areas, right? We would say that that plus that plus that plus that plus that better equals 0, right? Well, let's see. So the sum what is that? Negative 20. Do I have a second on that? Huh. Negative 20. Negative 20. It didn't add up to be 0. Well, let's be clear. These areas represent the integral of the shear diagram, right? And the integral of the shear diagram is the moment diagram, right? Now, we added these areas up and we got negative 20. Is there a moment that we didn't account for? What about that? And how much is that moment? 20, right? So the sum of these areas, in this case, because there's a concentrated moment, should be equal to the concentrated moments that we neglected when we drew the shear diagram. So they're not going to equal 0, okay? Does that make sense? See, for the previous problems, they did equal 0 because we didn't have any concentrated moments on those beams, right? Now we do, so we've got an imbalance. So the other thing about this, and this is one of the things that I always found confusing when I was a student, is, you know, when you're drawing the shear diagram, this load right here says 24.8 and it's pointing up, so you draw this up, right? But when we're drawing the moment diagram, does this cause an upward shift or a downward shift? It's like I never really understood that. And so for me, the easiest way to address that was to look at this. When I sum these areas, I get negative 20, right? But I want the sum to be 0. So in order for the sum to be 0, that has to be positive 20, right? So it is going to cause a positive jump on the moment diagram. It's going to jump up. Does that make sense? So let's see if I'm right, okay? So track my little guidelines. And one of the things I'm going to do is I'm going to draw a new guideline that goes like this. I'll put it in like red. And that guideline here is for where the shear diagram crosses at 0, right? Just so I know what I'm tracking. Ooh, I can do better than that. Hold on. Let me scroll down. It's easier when I got a little bit more room with my wrist. Okay, I'm not sure that was 100% better, but we're just going to go with it. And, oh, I forgot my little tick marks. Okay. We're going to start at 0, and let's see if we end at 0. Okay? Now, let's talk about this first region. Okay, this first region. We start at 0. How much do I jump up? 38.51. So I need to be 38.51. Now, we have two options. It's going to go like this or this. Which is it? One, exactly, right. A lot to a little. A lot of shear to a little shear. A high slope to a negative slope. That's the shear diagram. Or sorry, that's the shape of the moment diagram there. Now, if I'm at 38.51, what do I do from here to C? Like let's put our little de facto labels that we had come up with. So we had said that this was A, C, B, D, E. What about from here to point C? If I'm at 38.51, where am I going to end up? 2, right? So it's going to be like right there, right? And is it going to go, let's see, is it going to go like this or like this? 2. There you go. A little bit of shear to a lot of shear, little slope to a lot of slope. Oh, man, I can do better than that. Hold on. Okay, maybe I can't do better than that. Hold on. I'm going to do better than that. It's going to bug me if I don't. This is why I have a set of French curves. I can't do this by hand. Okay. That's about the best you're going to get out of me. So 2. Now, if I'm at 2 and I drop 222, where does that put me at point B? Say it again. Negative 220. And what does the shape look like from C to B? Linear. Yep, 220. Negative 220. Although that 0 looks suspiciously like a 6, and it's going to bug me if I don't fix it. That's better. All right. From B to D, what do I do? Wait, hold on. Where's the moment? The moment isn't there. It's at D. Yeah, so we ain't gotten there yet. But you're right. So 220 jumps up 100, puts me at negative 120. And then as you said, we've got to jump up. We have to jump up. Now look what happens, okay? See, we have to jump up because jumping up will put us at negative 100, and then the positive 100 will bring us back to 0. So it's like, it has to jump up, right? And also, we got that from this determination here. So jump up 20, bring us back to 0. Boom. Yes, sir.
Is clockwise always going to make it jump up?
That's a good question. I'm very hesitant to say, like, more often than not, yes, but I'm kind of hesitant to say that. The reason why I am is because of frames. When you have shear diagrams and moment diagrams going like this and every which way, I've always found that, like, the area determination is the one determination that is consistently applicable for beams and frames. That's why I'm showing you that way. Because typically what happens is we draw, like the way that I've always shown students how to draw frame moment diagrams is to do it in the order that you drew the member. And so you might have shear and moment diagrams that are like all over the place. That's why I like this determination. You are not off though in your conclusion for like beams, but I think it can result in some more confusion later. So. What do you think? Is this bad? Hopefully this is easy. It's just something a little bit more. All right, sound good? Okay. Now let's do something somewhat similar. And now for something similar, which is not what Monty Python would have said. They would have said now for something completely different. Any Monty Python fans? I have a feeling a lot of you don't know what I'm talking about, and it's breaking my heart. Do you know what I'm talking about?
Yeah.
Thank you.
I've heard of it, just never watched it.
My wife's heart is breaking right now if she were to listen to this recording. She's an avid Monty Python fan, and
I tried to get my younger cousin to watch it once, and it did not work.
there's so many quotable lines. Help, help, I'm being repressed. Okay, all right. Okay, we're going to compute the, all right, you can put a mistake, a 0.02 add to the mistake counter. That's 0.02.
That makes 4.
You mean 0.4?
No. 4.0.
We've been using scientific notation this whole time, didn't you see?
I have no.
At least I admitted it this time. I didn't blame it on, OneDrive not updating or something like that. We're drawing the shear moment diagrams for this beam.
Somebody else probably made this PowerPoint.
I can assure you they didn't. All right. Now, I kind of like this problem for concentrated moments because there's a little kind of riddle thrown in here, and I want to see if you're paying attention. But we did this problem before. There's also not just a concentrated moment, but there's an inclined load on this problem. This little 10 kips, right? We're going to talk a little bit about that here in a bit. But again, we've already computed the reactions for this problem. We got that a horizontal reaction is 6 kips, a vertical reaction is 28 kips, and a moment reaction is 480. Does that 6 kips matter? No. The reason it doesn't matter is not because it's horizontal, but because it is along the axis of the member, okay? So when we draw moment or shear and moment diagrams for frames, it's not like we're just going to ignore horizontal reactions because we might have a horizontal reaction for a member that's vertical, in which case, yeah, it does matter, okay? It's all about whether or not the load is along the axis of the member or transverse to the axis of the member, okay? Whether it's perpendicular, right? Does that make sense? I propose that if we had a member that was vertical, the vertical reactions wouldn't matter because it's going through the axis. Does that make sense? Okay. So we have a vertical reaction here, load, incline load. Interesting. See how we handle that. All right. All right. So shear diagram. Let's see what I do. Start at 0, and what do I do? Jump up 28. We'll call this point B and call this point C. Between point A and B, what do I see? Now what do I do?
3/4.
Oh, here we go. So you're close. You're close. Hold on. Let's talk about this. Okay, so this is a 3, 4, 5 triangle. So splitting this up into X and Y components, this is 4/5 of 10 kips. This is 3/5 of 10 kips. Only the vertical component generates any shear along the beam. So I propose we don't drop down 10, we drop down 8. So we are at 28, we drop down 8, and that puts us at 20. Now, before we go into the math, doesn't that just make sense? Because we're going to go constant, and then we see a 20 kip load that's going to bring us down to 0, right? So it's got to be 8, right? It has to be, you know? I don't like using that type of logic to construct shear diagrams, though, because you start getting into self-fulfilling prophecy land. It's like I have to figure out how much the drop is so that I get to 0, but it's kind of backwards because you're starting the problem based on this jump, and this jump has to be correct in the first place. So it's like I don't like using that logic too often. Does that make sense? Okay. Let's see. I'm not running short on time, am I? No, I'm good. We're actually going to be kind of early today. All right. Let's do some areas. What is the area of shape 1? Say it again. 280? Positive 280? What about the area of shape 2? So if I sum the areas, I don't have any negative area at all, right? There's no negative area. It's just that and that. But when you sum those up, what do you get? 480. Which means the following. Come on. When I start my moment diagram, what is the very first thing that I see when I draw my moment diagram? What's the very first thing I got to deal with? The 480 foot kips. And which direction do I draw that? Down. I draw it down because these areas have to bring me back up. So negative 480. And then this jumps up to 80 to negative 200, and then that goes to 0. Both of these regions, by the way, are linear. My hand is wavy. So what do you think? That's not bad, is it? I will give you a little bit of a taste of what we're going to do next time. Before we start talking about frames, there's one thing that we haven't covered. What haven't we covered? We haven't covered internal hinges. And do you want to know how an internal hinge affects the construction of a shear and moment diagram? It doesn't. It doesn't, okay? The reason why is because the internal hinge, and we'll talk about this next time, but the internal hinge provides an equation of condition. And it's that equation of condition, that extra piece of information, is what we use to solve for the reactions. I propose that whenever you're constructing the shear and moment diagram for a beam with an internal hinge, you ignore that internal hinge as if it doesn't exist. And what will happen is that if you've done it correctly, when you draw the moment diagram will be 0 at the hinge. That's what I propose. So whenever you're drawing a shear and moment diagram for a hinge, you just ignore that hinge as if it doesn't exist. That doesn't mean you don't use that hinge when you're computing the reactions. All right, a couple other things. Number one, I wanted to give you a little bit of a heads up on some scheduling items for next week and the week after. So we are going to have in-person lecture on Monday. We're going to talk about internal hinges. We're going to have in-person lecture on Wednesday. We're going to do frames. We're going to do shear and moment diagrams for frames. For Friday, we are not going to have in-person lecture, okay? We have green and white day on Friday, and I'm the AD, so I got to go do that, okay? We are also not going to have in-person lecture the following Monday. So the 15th and the 18th, we are not going to have in-person lecture. I'm going to have pre-recorded lectures that I post to YouTube. The reason for Monday is because Monday we have our regular periodic ABET review that day. So we are all going to be pretty busy, at least myself, I'm going to be pretty busy. So I'm going to just pre-record those lectures in advance. You are not going to have a homework assigned on the 15th to do the 18th, but you are going to have one assigned on the 18th to do the 20th. So for those 2 lectures where I'm pre-recording them, I'm taking off one assignment. Like I'm easing up on one assignment. I also checked our schedule as to how we're progressing throughout the semester in terms of like, are we making forward progress and are we falling behind? We're actually very good. One of the things I think I'm going to do, though, is for the second exam, I think I'm going to push it back 1 lecture. So instead of it being on the 27th, I think I'm going to make it on the 29th because there's a deflection lecture that I gave last year, and I basically called it like tips and tricks for deflections. And in the end, I think that the class really benefited from that. And I don't have to do that lecture, but I really think it would be a good idea if I did. So I think I am going to do that and push the lecture back or the exam back 1 day. Okay. So I think we're actually making pretty good progress in rocking and rolling. Trying to think if there's anything else. I can't think of anything. Anybody have any questions? Well, it is 10:41. You get out 9 minutes early. You have a wonderful weekend. We will see you on Monday.